Today we are going to look at Newton's shell theorem, which describes the gravitational forces that are exerted by spherically symmetric shells on objects. The shells could be hollow or solid, and there are really some nice implications to this. This derivation was first demonstrated by Newton himself using his theory of universal gravitation. So in this video, I'm not going to go through the derivation. We are just going to look at the statement of the theorem and then discuss about the interesting implications. So really stay to the end if you want to get a full understanding of this theorem. If you're interested in having the derivation, then let me know in the comments, and we are going to make a video dedicated to the derivations of this theorem. Okay, let's go. So suppose in the first case that you have a body that's outside a shell, a spherical shell. So let's say case 1, body outside a shell. So I say shell, but in this case you can imagine that could be a hollow, it could be a hollow shell or a solid sphere. So let me just say hollow or solid sphere. Either cases, we can put both situations in this first category. So let's say here we have a mass, spherical mass. It could be hollow, it could be a solid sphere, but it's a spherical object. It has a mass of m. You can imagine it's a planet, for example, and then it has a radius of small r. Then let's say at some distance you have an object, let's say u. I'm very good at drawing, but this should be fine. Okay. Then the Newton's shell theorem in this case states that the gravitational force exerted by this mass, capital M, on the body, small m, in this case, would be as if the mass was concentrated at its center. Which means, if we suppose the distance between the center of mass of this body and this body is d, so let's say this is d, then this body is going to be attracted to the planet, in this case, as if that planet was a point located at its center of mass. So what this implies is that the force exerted by the planet and the body is going to be, let's gmm, I'll just write the magnitude of the force, all over d squared. So it will be like this planet is a tiny point, you can see, a tiny point located at the center of mass, and the distance between the center of mass of this planet and this object is d. So it's like you are having 2 points that are gravitationally interacting, and the expression of the force of attraction is given by this equation. That's just Newton's universal law of gravitation applied to this situation. Of course, this result can be proven by integration. It's not just a guesswork. We can show that, but I want to do that as I earlier mentioned in this video. So that's the statement of the theorem for the first case, when we are having the body outside the shell. It's really straightforward. Then we can have a second case where we are having the body, an object inside a hollow sphere. So this first case works for a hollow sphere or a solid sphere. But here we really assume the case of a hollow sphere. We are having a body placed inside. So let's say here we have a sphere, like that. Oh, nice circle. And here we have the center, and we're having a small object that's placed, let's say here. The small object is of mass m, and you have your sphere, of mass capital M. It's much bigger in any way. And this is hollow, I should mention that. Then we can show also by integration that the force, the gravitational force exerted by the sphere on the object small m is 0. So this object has like the mass has no influence on the tiny object small m, which means if it's placed, if the object little m is placed there, it stays there forever. It experiences no force. And what this implies is that the potential is constant. The gravitational potential in which small m is just a constant anywhere inside this shell. Another way to picture this is just to imagine that each portion of this, change pen, so each portion of this, let's say you have a portion here, it's going to exert a gravitational force of attraction on this mass. But then since the sphere is symmetrical, you can imagine that you have another portion that's symmetric to this one down, and it's also going to exert the same force. Okay, you can also picture you have a point, a portion of mass here that exerts a force, and you have another one here that's symmetric to it that's exerting another force. So in total, when you're going to sum up all the forces contributed by each portion, it's 0. So it's really kind of intuitive. And then the last case, which is the most interesting one, let me change paper, is when the body is inside a solid sphere. So inside a solid sphere. So here we are going to treat an ideal case. We suppose we have a solid sphere. So picture out just a planet that has a uniform density. So make it a little big like that. Oops. Okay. So imagine this is a planet. Okay. That's the best example we can take. This planet, it has a uniform density. So uniform density. It has a mass of m. Then we suppose we have our object that's just here, a tiny little object right here, that's at a distance of small r from the center of mass of the planet. The planet itself having a radius capital R. It's true that my sphere is maybe not perfect, but okay, that should be fine. All right. So let's say we want to calculate the gravitational force of attraction exerted by the planet of uniform density on this object. So here is a planet of uniform density. Then, according to the shell theorem, or a consequence of the shell theorem, is that the portion of the mass, so let's say we have, we can draw a concentric sphere to this one, like that contains this object. Hope you can see that. So we imagine an imaginary sphere that's concentric to the main one, and that has a radius of small r. Then, since the shell theorem tells us that if an object is inside this sphere, like that, it's going to have a 0 force. In other words, the portion of the sphere that's outside of this small radius, small r, has no influence on any object that's inside this object. So this part, this portion, already has no gravitational influence. So we put that out. This means that if we want to calculate the force exerted by this mass on this object, then we should only consider this inner portion, this one here. Okay, so let's say F in this case, it's just going to be G, I'm writing the modulus of the force, then M contained in this radius R times the mass of the object itself, which is small m, divided by the distance that separates them, and that's R squared. Again, this expression is a consequence of the first theorem which we saw, which is that the force that the object little m is going to feel from the planet, in this case having a mass m of small r, so the one in dotted, the shaded inner portion here, that's just the force exerted by this inner portion, and it would be like the inner portion is concentrated at the center of mass, and we are having the gravitational force exerted by this point on this object. So it's g m of r, small m, divided by the distance that separates them. But since the planet is of uniform density, then m of r, density is mass on volume, so mass is density times volume, so that is so that's going to be rho, so the density times the volume, 4/3 pi radius cube. So this is going to be the mass of this dotted portion. And if we insert it above, we're going to have at the end 4/3 pi g rho m and r. But then, according to Newton's law, this is equal to a mass times an acceleration. So it means that we can say that the acceleration, if the m's cancel, we have that the acceleration is 4/3 pi, so 4/3 pi g rho r. So of course here I have neglected the unit vectors, but you could imagine that there was a unit vector E of r like this, in which case I would put a minus here, I'll put a vector here, and I'll put ER like this. Or if you prefer, I can say that R dot dot is negative 4/3 pi g rho r. Okay. And this result is very interesting because if you look at it keenly, then it might probably remind you of something. This is actually the equation of motion of a body that undergoes simple harmonic motion. A body undergoing simple harmonic motion has an acceleration, this represents the acceleration, that's proportional to its displacement, and the constant that links them is just negative omega squared. So this expression is the equation of motion for a body undergoing simple harmonic motion. So what this implies is that this body, little m, in this case, performs simple harmonic motion about the center of the sphere O. In other words, if this body is released at this location, then it's going to perform oscillations like this. So it's going to move up and down, like that. And we can go further to calculate the period of these oscillations. Omega here is, so omega squared would be just the coefficient, so this term, so that's 4/3 pi g rho. So we can get omega, and we know that the period is 2 pi on omega. And if we do that, I think that's 2 pi square root of 3 on 4 pi g rho. So this is the period. This is the period at which this body oscillates. It's going to move up and down, up and down. And also what's interesting about this motion is that the body reaches a terminal velocity at this location. At the center, this is where the velocity of the body is going to be maximum. Because at that point, r is 0, so the acceleration r dot dot is 0, which implies that the velocity is a maximum. So this, we really have here all the characteristics of a body that undergoes simple harmonic motion. We have a period, we have a maximum velocity, we have oscillations. I have to admit that the first time I really fell on this result, it was really fascinating to see that a gravitational field, which we picture as making objects revolve, orbit, can also make objects to oscillate, just like a body, a mass attached at the end of a spring, or a simple pendulum, because this is really what is described here. Let me know about what these inspire you in the comment sections. But yeah, this is really very interesting, and these two theorems simplify a lot our calculations and understanding of gravitational fields. So far we are in non-relativistic situations. If we go to relativistic cases, then things become a little different. So hope you find this interesting. If so, drop a like after subscribing, and yeah, drop a comment and share your thoughts. Feel free. Until then, I see you in the next video, and do not forget that physics is believing that a simple and consistent description of nature is possible. Thank you.